Thank you very much. It's a real pleasure, and it was a real pleasure to meet you, Rob, at the DMA Awards. Thank you, Corrigan, for the help. Thank you for inviting me. So I'm going to be talking you through some of the field guide stuff. So at a bank, obviously, we had to take a very practical and pragmatic approach to how are we going to do this? We had to take these ideas, these changing in standards, like FIPS has changed. That's huge. And Constantinos has done a great job at showing you that the kind of mathematics that we're changing to, my background's in mathematics. I'm going to show you what we've been doing sort of activity-wise and how we're approaching it from a kind of a strategic point of view, as well as some of the more practical things that we're trying to do, some of the tools we've written, and walk you through some of the ideas that we're trying to sort of get across from our perspective. And so, why are we here? Q-Day is coming. And this is a very sort of big headline, but it sometimes can feel a little bit nebulous. So we try and sort of narrow it down a little bit as to, okay, what do we mean by that? Well, what things are being affected? And a previous speaker, Marin, has really covered off like so much of our tech is reliant on good cryptography to be effective. Lots of notions of identity, of safe storage, of secure transport of information. They rely on cryptography. Some things don't, data classifications probably won't go PQC, and that's fine. But other things like sort of tunnels, encrypted storage, key management, they are going to undergo a significant amount of change. And so we say Q-Day is coming. When? And one of the earliest estimates is actually April the 14th, 2030. Now, Cloud Security Alliance published this. Many agree, many disagree. I'm on the more disagreeing side, I think. But as Konstantinos mentioned, like it doesn't really matter. Actually things are just changing in the standards. So, maybe you don't take that Sunday working too far away from the office because that's the 14th of April is actually a Sunday. Maybe what we do is we take this date and I'll illustrate how we think about this in a regulatory frame or point of view. So this is 2030, end of, visualized by data retention requirements. So if you're familiar with Mosca's theorem from Professor Michaela Mosca, CEO at Evolution Q, he has this idea that your risk time is your time to convert your cryptography plus your data retention time. And if it takes you longer to fix things, that it does that quantum computing to come about, then you've got a problem. And what does that problem look like? Well, certain types of data we don't keep for very long. Commercial data is kept for about 4 years. But things like tax records, financial records, like it's a fiduciary responsibility on the bank, certainly in the EU and UK. The UK regulation for reference is 6 years from the end of the financial year in which that data was generated. So 7 years to be safe, right? Now, that is still a longish time, but some things we want to make digital, like CBDCs, they have to have lifetimes that will go into the decade. And it doesn't matter what you think of quantum threats now or soon, right? The quantum threat, something will happen. If it's going to happen, it'll probably happen within 50 years. So how do we mitigate that? How do we manage this in an organization? We've already covered over what's in this slide, so I won't spend long on it, but we do have a new key exchange and we have two new signatures that we have to start at least investigating and trying to work out where we're going to put them. Okay. Now, key exchange will probably be a bit more straightforward to fix. We update to OpenSSL 3.5 and beyond. We update Chrome and Firefox. If you're using Chrome and Firefox, Chrome 132, Firefox 131, you're already using hybrid PQC by default, or at least you're trying to. If you connect to a website protected by Cloudflare or Google, you will negotiate a PQC handshake. And you can see that in the traffic. So what we're trying to do is go, okay, how do we actually get to the point of the real benefit of all of this? Because it sounds like we're just making more work, but I promise you there's a benefit. And there's one slide that sort of lingers in the mind. Let it be this one. Okay, we don't know what cryptography we have where. That's a big problem, mainly because we've never really considered cryptography to be a malleable asset class. So we're asking ourselves to change something that we haven't usually thought about changing, except when we, rejig a server or take something down and put the new version up or upgrade software. Like now we have to much more consciously handle it. So first of all, we have to do is a discovery exercise, and Marin covered that really, really well earlier. But what I'm trying to push is to get into an OODA loop of quantum, as a post-quantum OODA loop. So what does that look like? We take this discovery, we relativize it to the new standards, and then we start making decisions. Okay, I've got a critical data flow over here. I'm going to start there. and I'm going to worry about this development flow a little bit later. I will get there. I'm going to roadmap it, but I'm going to first of all organize my activity, and then I'm going to go and do it, and then I'm going to go into a monitoring phase. So we're going to see an OODA loop for cryptography come out, and I think that's a brilliant thing. We also get all these other benefits as well. If we have agile cryptography, then we could automate a lot of it. Imagine a world where you never have a certificate going out of date and expiring, and you can't find it, and production is threatened. Imagine where actually we know where it is, we can just go and fix it. We could better audit cryptography, where we look at things like PCI DSS, like a huge requirements, DORA in the EU, new regulations, like huge requirements on actually cataloging cryptography. Same thing in the US as well. So that becomes easier if we do this particular activity. Likewise, if there are new threats, we can respond better and faster to them. Now, the data model we're going to have to get used to is something called a cryptographic bill of materials. We're going to have to build these records. But how are we going to build them? Where do we get the data? The first step is to realize actually we already have many of the tools that we need to start the job. If you have a scanner like Qualys or Nessus from Tenable, then you can start looking at bad ciphers that have been found, bad or out-of-date certificates, things that we know are bad, so bad they're actually vulnerabilities. Okay, you can start there, and you can start the journey already to start aggregating information and going, okay, I have this. What more do I need? And you start getting into that flywheel of discovery. Where we want to look at two fronts, really, which I'm going to cover here today. The first is really code. How do we find cryptography in code? Because if it's in code, it can be executed, and that's where we need to start managing our performance and managing our actual usage. And you might go, oh, regex, it'll be fine. And there are two really good arguments against this. One from Java, triple des, which is deprecated long ago. Like that is spelt several different ways: 3DES, TDES, triple DES. It's not standardized. In Python, you have a thing called Fernet. It's a cipher in the main cryptographic library. It's AES 128 in CBC mode, but it isn't spelled that way. It's spelled FERNET. So you have to have a different approach. And the approach that we went for is first of all acknowledging, okay, there's all this variability, API variability, data flow complexity. These also lead into the fact that we don't really have a good abstraction model. So we worked with Microsoft and GitHub to find a way of teaching a tool called CodeQL about cryptography. Now, if you've not used CodeQL, like it's really robust, it's really good at static analysis, it scales really well. It essentially takes your code and turns it into a database that you can query. And it supports a really huge range of languages. And what it lets you do is this. You can have a query, and this is a readable query. What does it say? Take some cryptography, asymmetric, ignore the elliptic curve, and then find all the keys less than 2048 bits. And those are keys that shouldn't be around now. When we get to having to migrate to post-quantum, the job will get much, much easier. And we could do it with CodeQL. So likewise, this is a slide just to show you some links. We released this at Black Hat Europe in 2023, and we've been building on it ever since. It's now built into GitHub Advanced Security, for example. So we're happy to swap some questions and some ideas if people want to over Slack. The next thing is to look at how cryptography works in transit, because we get good visibility on those two. We can find all of our code and we can do things with it. We can also inspect traffic and find out what's actually going over the wire. So to do this kind of more dynamic and behavioral analysis of network traffic to find cryptography. But first of all, we have to go, okay, how do we do this? Normally we draw a diagram, we say, okay, here's a server, there's some requests, there's some data API calls, and then there's some administration, and that's how we draw it, but that's not how it happens. We all know this is the actual topology. There's some switching, so infrastructure. Now, that infrastructure is designed to be monitored for various reasons, performance and otherwise. If we take a span tap or a tap port on our data, and we just pipe it into a sensor, we called it cryptographic monitor or cryptomon, then what we could do is we could utilize existing technologies to be able to inspect some of that traffic and start getting out some useful information. Now, you might guess how we're doing it. We're using eBPF. If you've not played with eBPF, it is one of the most wonderful things. You write a little blob of code, it gets compiled to a fixed runtime, and it get and a fixed length, so it's and it's very safe to put into the kernel. It gets deployed in the kernel, and you can get all sorts of process metrics out, all sorts of amazing data. And so what we did is we came up with a tool. We took an Ubuntu system, we gave it a little C module that does the initial inspection, that gets compiled and loaded by a Python orchestrator. We analyze it in Python, and then we pipe it into a database. And this allows us to have a very flexible, very malleable sort of setup where we can just put the monitor on different span taps around the organization. We can start aggregating data. So I can tell you, for example, in the lab I'm sitting in, around a quarter of our traffic is already starting to be hybrid PQC for certain devices, which is impressive. And I know that that's the case. So now I can start building, okay, where do I need to change things? The things we look for, okay, TLS, big one. Port 443, port 8080, 8000, but also 3389. RDP is a TLS protocol. So is FTPS on port 990. We also look at SSH over port 22, and then we capture keys, cipher suites, handshake information, and we start aggregating it so that we can start analyzing it. I won't go into more on that right now, but here's some links so you can find out more on as your interest takes you. These are all open source tools. We want people to get on board and start helping the community build these tools out. So something I really want to talk about is our cryptographic standard. Now, I can't show you it live because it's a controlled document, but what I can do is show you the kind of skeleton of what's going on. We put it in GitHub. And this was really difficult at first, but actually it's proved to be really, really useful. So we organized it in three places, cryptography first. And that's like, okay, do you or don't you want to use AES 256, AES 128? What cipher modes do we accept? That kind of thing. And then from there, we go into the implementations. So we try and line up SSH, we try and line up TLS cipher suites that are approved in Apache, in whatever. And then what we do is we create the configuration files or the blocks of code that are normalized to the standard, and we put those next to the reference documentation so that you can see, okay, here's what that should look like in code. And then whilst we go for cryptography, then implementations, and then into key management, like how are we going to do that? Like key exchange, we'll fix as we go along and update things. But if we end up doing PQC key management, PKI might significantly change. So the whole push of getting it into GitHub is to give accessibility. It also gives us a full chain of evidence as well. For any line, someone can go into it and they can go, oh, who wrote this? Which PR, which pull request pulled this in? Who approved that? What issues were they trying to solve? All that information is captured. And GRC, so for those who don't know, governance, risk, and compliance is how you spell God in finance. So GRC love it because they can go git blame and they can find out all this amazing information about the standard that is there. And this is a way of making, standards as code, making it more agile. It takes, a small village of people sitting, and I'm a mathematician. I work at Santander. I also am the co-founder of Quantum Village at DEF CON. And we try and get people to think about these things in new ways and to find all these new approaches. So we're really excited to show you this. And the closing remark is really, securing our digital landscape really does take all of us. It's finding the champions in the right places in the organization so that the right tools can be implemented in the right place at the right time and inform the right conversations. And it's been really great to share this work with you. And thank you very much for your attention.